Hey everyone, let's take a look at two problems in 10.1, numbers 5 and 6. In both of these, we're going to determine the limit of the sequence or state that the sequence diverges. Of course, it will be divergent if the limit of the sequence either does not exist or is infinite, plus or minus infinity. Okay, the first sequence, here's the general term or nth term of this sequence, a sub n. And so we want to take the limit of that. So I'm going to show you a few different ways. We've talked about it in class, but some different ways are helpful to see what's going on. One way to handle this is, of course, we have this important theorem that says if I have the limit um, of, I'm going to do n going to infinity of, some constant, we'll say c over n to some power, and let's say r here is some positive exponent. And we talked about the fact that if c is some constant, then the denominator getting larger and larger, this ratio is getting closer and closer to zero. In fact, the limit is indeed zero. And we're using a lot of the limits at infinity that we found for functions of real numbers. Sequences are functions of just the positive integers, typically. So um, then we are going to basically essentially pass the function through these points, and the formula for the function would look the same. We might create a function f of x, right, which is 9 plus x minus 2x squared, etc., and then do all the same limit laws and things that we were using when we were taking limits at infinity way back in first semester calculus. So I'm not going to change to the variable x. We'll treat this like a function. So first of all, one way to find this limit in order to make use of this important limit here is when you have a ratio of polynomial functions, look in the denominator at the highest degree term, which is n squared, and divide the numerator and denominator by that n squared. So here I'm going to divide each of these three terms by n squared. So I get 9 divided by n squared. N divided by n squared simplifies to 1 over n, and 2n squared divided by n squared is just 2. Here, dividing by n squared, I get 3 plus 1 over n squared. And again, I can multiply by this because this is equal to 1, and we're guaranteed n is not 0 because we're taking the limit as n goes to infinity, so we're certainly looking at positive values of n here. So when we do this, though, notice this fraction here, 9 divided by n squared, is like where c is 9 and r is 2. That is going to go to 0. 1 over n, that's going to go to 0. 1 over n squared, that's going to go to 0. And what are we left with? 0 minus 2, we get negative 2 up top. 3 plus 0, we get 3. And our limit is negative 2/3. Now, the way we thought about this in class too is if you look at a ratio like this, notice the limit is the top is going to minus infinity, the bottom going to positive infinity. So essentially, we're in the form infinity over infinity, which in general is indeterminate. But if you take for large values of n, the highest degree term in the polynomial in both the numerator and denominator are going to dominate. And in fact, the limit of this rational expression is equal to the limit of the ratio of its leading terms or highest degree terms. So up top, that's negative 2n squared, and in the bottom, it's 3n squared. And now this limit, so the limit of this function will be the same as the limit of this function, this ratio. And I can simplify, notice, very easily down to negative 2/3. And now the limit of a constant is just negative 2/3. Of course, we get the same result. So either way you do it, you can use that. Or if we think about them again as being functions of real numbers passing through the points of the sequence, this form infinity over infinity, remember we can use L'Hopital's rule. And I'm going to use the L for L'Hopital. And when we use it, remember how that works. It's the limit of what? The derivative. So we're thinking of this now as a function of real numbers. So take the derivative. I'm going to do it with respect to n. Derivative of 9 is 0. Derivative of n is 1. And derivative of 2n squared, bring the 2 down, we get 4n. Here the derivative is 6n. Derivative of 1 is 0. So I look at this, and again, it's still, I guess, minus infinity over infinity as n goes to infinity. It's still indeterminate form. Well, no problem. We could use L'Hopital's rule again. Derivative of the top is negative 4. Derivative of the bottom is 6. limit of a constant is just the constant, negative 4/6, which simplifies down, of course, to negative 2/3. So any of these three approaches are fine. This middle one here is certainly quick, and you can use that. I would expect you to find limits of the ratio of polynomial functions fairly quickly. Okay, number 6 then is similar to number 5, but it's not a polynomial function down here. We can still make use of two of the methods rather up above. One thing is the highest degree term in the bottom is n cubed, but it's under the radical. So it's really n cubed under the radical, or n cubed to the 1/2 power. Multiply the exponents, it's really n to the 3/2 power. So if I divide both the numerator and denominator by that power, what happens? Well, here I get n divided by n to the 3/2. And here I'm going to write it in the form, because this is under the radical, I'm going to divide it by this form, which is the same thing as n to the 3/2 power. And the reason I do that is if we have, right, the square root of a divided by the square root of b, that is the square root of a divided by b. And that's what I've done. I've written it this way, and then divided both n cubed and 12 by n cubed, right? Distribute that through. Simplify n divided by n to the 3/2 is just 1 over n to the 1/2. And then, of course, n cubed divided by n cubed is 1. And now I take the limit as n goes to infinity. And notice this fraction here is going to 0 because 12 over infinity is going to 0. And here, the square root of n goes to infinity as n goes to infinity. So this is 1 over infinity form. That's going to 0. And what we're left with is 0. 1 plus 0 is 1. Square root of 1 is 1. So this ratio, 0 divided by 1 is 0. So the limit is 0. We could also have just taken the highest degree terms, in a sense, n up top, obviously. And then what's the highest degree term in the bottom? It's, really be careful, n cubed under the radical. So it's n to the 3/2 power. Simplify that down, which we did above. Just 1 divided by n to the 1/2. And as n goes to infinity, that's going to 0. By the way, L'Hopital's rule, not helpful like it was in number 5. Here, you kind of bounce back and forth. This radical expression kind of bounces up and down each time you take L'Hopital's rule. Doesn't really help in this case. So again, there's a variety of methods to finding these limits. I hope these two are helpful.